All right. Looks like we're ready to start. So what we have to do today, morning, and it is quite early. Well, where's all that snow we were hearing about? I guess it's coming. Supposedly it's going to get really ugly today and tomorrow. But we'll see, won't we? All right. Well, we're home. What's the big deal? But anyway, yeah, so what we have to do today is look at the second problem set from chapter 5, which we finished the first one last time. In fact, why don't we go back and visit Moodle for a second? Yes, our old friend Moodle, and see what's going on here. Okay, so we have problem set number 2 waiting for us. Number 1 is done, so that's good. All right, here's number 2. Let's open it up. Sorry about that. All right, and if we finish this, I think we will. This one is long, but it won't take that long. We'll get this one done. Then we can get back and finish chapter 5C, where we were in our middle of our discussion about sequences. Okay, let's go back here. Hold on 1 second. Oh, I've got it open twice. That's why. All right. Yes. So anyway, so 5C is right about here. There we go. And here, so you remember that we were getting close to the end. Actually, no, wait a minute. Hold on a second. Where were we? That's right. Okay. Yes. The very last topic in this chapter is sequences. And so we're not quite done. We just barely started it, basically. And so we'll try to finish that. And then we'll be done with 5, and then we can start 6. If we're really ambitious, we might be able to start 6, but maybe not. All right, let's see how it goes. All right, so let's get this one going. And let's see what's going on. Okay, here we go. All right, so these first few are just basically short fill-ins when you look at them. And you'll notice the first one asks if the square root of 49 is rational or irrational. And so how do we answer a question like that? Well, you might recall that the rule with square roots is very straightforward. Since 49 is a perfect square, its square root must be an integer. Therefore, the square root of 49 is rational. Okay, now it doesn't say, you must prove it or anything like that, but that's why this is happening, because when you take the square root, you can see that it is 7, which is obviously a rational number because it's an integer. But on the other hand, let's take a look at this one. 2, radical 37, since 37 is not a perfect square, its square root is irrational. And that's all you have to remember. Perfect square, the square root is rational. Anything else, the square root is irrational. Now, this one's a little tricky because if you look at it, you might say at first glance it appears to be a repeating decimal, but it's not, because look what's happening. You've got 0.23, 0.233, 0.23333. So it's not repeating. Repeating would mean, for example, that it's always 0.23, 23, 23. That's not happening here. So therefore, since this is not a repeating or terminating decimal, it is irrational. Okay, so that's all we need to know. Is it repeating? No. Is it terminating? No. Therefore, it must be irrational. All right. Is 5, 6 rational or irrational? Well, since it's a ratio of 2 integers, it must be rational. That's because that's what rational actually means. Okay. Now pi, we know, we don't have to explain it. I mean, it's understood. Pi is irrational. End of story. Now 0, on the other hand, remember we mentioned this early on as a special case. 0 is rational because it is an integer and it can be expressed as many different ratios of integers, such as 0 over 1, 0 over 2, 0 over 3, etc. So it is considered to be rational. Okay. Okay, now the fun begins. Simplifying radicals. Now, keep in mind, sometimes a radical can't be simplified. There's no guarantee that it can be simplified. And if not, you would just say, I mean, the answer would just be, like, for example, the square root of 13 can't be simplified because it is a prime number, and the square root of 13 would be your answer. But here, basically your strategy is to find factors of this number, of which hopefully one of them is a perfect square. If that can't be done, then realistically, you're probably not going to be able to simplify it. So this is the same thing as 4 times 6, which is very fortunate because, of course, 4 is a perfect square, and so we end up with 2 radical 6. And we're done. We can't go any further because 6 is not a prime number, but it can't be broken down into any factors which are not prime. All right, well, that one is good. Now, how about this one? All right, let's see what we can find in here. Oh, I know. How about 3 times 9? Or let's write it as 9 times 3. Yeah, that's nice. And the result will be 3 radical 3 is the simpler version of radical 27. Now, 80 is an interesting case because there's a few different ways we can go about this and still get to the same result. But the quickest way is to write it out as 16 times 5. Now, you'll notice that we could also have written it as 4 times 20. If you have more than one factor, which is a perfect square, what you should do is start with the largest one, because that'll just save you the most steps. Okay. If you started with 4 times 20, you would have eventually gotten to the right answer, but this is just a little bit quicker. So you're going to end up with 4 radical 5. Now, this next one is a little bit more challenging, but you might notice if you look at it long enough that one of its factors is in fact 25. That's right. This is the product of 25 and 7. And that worked out beautifully for us. All right. Now, how about 30? Well, 30, unfortunately, I mean, you can write out all the factors that you like. 1 and 30, 2 and 15, 3 and 10, but there are no perfect squares in there. So the answer here is that you just leave it at the square root of 30 and you're done. There's nothing else you can do. Okay, now 42, it's surprisingly enough, the same thing happens here. If you write out the factors, 221. What else is there? 3 and 14. 6 and 7. That's it. There's nothing we can do with this one. So we just leave it and you're done. And that will happen sometimes. All right, here's a few more simplifications. Now here you've got, it's a little bit more complicated. There's a constant out here, but guess what? That doesn't change the basic idea. Here I'd like to change this to 4 times 5. because the 4 is a perfect square. And that's 10 times 2 times radical 5, which is 20 radical 5. And you're done. Very good. How about 4 radical 8? Well, let's see. The 8 has as its factors 4 and 2. What do you know? So we'll have 4 times 2 times radical 2, and we end up with 8 radical 2. All right, now this one is interesting because you have a perfect square as a factor of 700. Oh yeah, look at that. It's 100 times 7. How convenient. So you have 3 times 10 times radical 7. Oops, let me clean that up a little bit. And that finally turns into 30 radical 7. All right. Now, what about this one? Okay, let's find out. All right, I have an idea. How about this? 81 times 2. There we go. Because, of course, we know that 81 is the square of 9. And so the final result is 18 radical 2. All right. So we're starting to get pretty good at this stuff, aren't we? Yes, we are. Now here, in these cases, we're applying the rules that we learned that you can multiply 2 radicals together and consolidate them as a single new radical. And once that's done, you can then maybe simplify it. The key word there being maybe. Now here we saw earlier, radical 20 was actually one of our earlier questions, wasn't it? I thought it was, or it was part of another question. And so, so what do we do with this one? Here we go. This is the same as 4 times 5 under the square root sign. So we end up with 2 radical 5. Very simple. Nice. Okay. Now, how about this one? So we'll start by multiplying it out and seeing if there's any obvious candidates for a perfect square factor. Yes. Look, 9 times 10. And so that ultimately turns into 3 radical 10. All right. So that you can see these really aren't that difficult. It's just that sometimes it may not be obvious how to break them down into something more convenient. If it's not clear, you can try writing out all the factors. For example, with 90, just start to make a list. And if you come across a perfect square, then you should use it. And if there's more than one perfect square, choose the larger of the two, because that'll speed things up a little bit. Beautiful. Now, how about this one? What is the product of 18 times 15? Well, that actually works out to be 270. And guess what's hiding in there? A 9. Okay, now we saw earlier, we definitely had 30. Let's scroll back for a second. This one, we saw earlier that the square root of 30 cannot be simplified any further. So you can see here, we have the square root of 9, square root of 30. And we're done. We cannot simplify radical 30 any further. Now this one, here's what you can actually do. You don't even have to, all right, let me show you two different ways of doing this. You can go ahead and multiply it out. And then you would say, oh, wait a minute. Isn't this 25 times 5? Of course it is, because we saw that over here. And we're done. But what you could also have done is just said, oh, this is just 5. And then normally in a case like this, you would try to put the constant, the non-radical first, and you would have ended up with the same answer. It doesn't matter which one you do, but you'll see that you will in fact get the same answer. Okay. Now, what about these guys? Well, when you multiply these together, you're multiplying the constants first, the coefficients, I should say, and then these get consolidated together. So first, you're really just rearranging the order so that you can see that this becomes 6 radical 48, and then the 48 is itself 16 times 3. And so we end up with 6 times 4 radical 3, or 24 radical 3. And that's our final answer. So sometimes this multiplication brings us to a nice simple result. Sometimes it doesn't. It's not always possible to simplify them. That's okay. We do what we can. All right. So how about this one? So we'll multiply these coefficients together. And then the square roots are 15 and 5. So we have 12 radical 75, 75, which itself can be rewritten as 25 times 3. Twelve times 5 radical 3, 60 radical 3. Okay, that's it. We're done. All right. Okay, so now we're getting ready to go into the ratios. And the ratios are, not difficult. In each case, we're simply creating a single new radical. And in many of these cases, we'll be able to simplify the final result. So this is the same as radical 60 over 2. Now, we saw earlier that radical 30 can't be simplified any further. And so we're done with that. Radical 30, and that's it. We're finished. All right, what about this one? So sometimes, like in this case, we're going to wind up with radical 42 over 6. That's it. 7 is a prime number, and so we're done. We cannot make it any simpler than that. Now, in this case, we know that the ratio of 64 over 8 is simply 8, and this can be rewritten as 4 times 2. Okay, that's it. We're done. All right, now how about this one? Now, you can see pretty clearly that this one is going to reduce to radical 5. Radical 5 is prime, so we're done here. Let's make this a little neater. All right, there we go. All right, so far so good. So these are all pretty straightforward. I think you'll agree. Now we're going to get ourselves involved with addition and subtraction of radicals. And of course, remember the key here is that you can only apply addition and multiplication when we have the same radical in both cases. All right, so here's an example. We have, since these are the same radicals, we can add these two together. And we simply end up with 12 radical 7. Very good. And that's really all there is to it. There, in this case, there's nothing that can be simplified because 7 is a prime number. Same thing here. What we actually have here is 50 plus 11, radical 11, which is 61 radical 11. Very nice. Okay. And so here we have 8 minus 15 radical 3 minus 7 radical 3. And that's it. Now, some of the next ones are a little bit more challenging because, well, you'll see why. Because let's say, for example, this first one. On first glance, you might say, you know, I don't think we can combine these, but watch what happens here. 320 is 64 times 5. And 80 is 16 times 5. So you've got here radical 64 radical 5 minus radical 16 radical 5. And you can see where this is going, I think. You've got 8 radical 5 minus 4. Oh my God, they can be combined and simplified at the same time. Nice. But of course, you know, it may not be obvious right away, but you should be able to tell right off the bat, they're both divisible by both 5 and 10. And that should give you a hint as to what might be possible. Now, that doesn't guarantee anything. You still might end up with two things that can't be combined, but you can at least try different possibilities until you see if there's something that can be done. Okay. So in other words, look for common factors between the two. They may not be there. Like if, for example, I had radical 5 minus radical 3, I could not combine those. That would be it. I'd be done. Okay, so we have same thing here. Both of these are have a factor of 5. Let me make that a little neater. And over here, of course, we have 4 times 5. All right, let's see what we've got. Okay, so we end up with 5 radical 5 minus 2 radical 5. And of course, that leads us to 3 radical 5. Oh, sorry, I just realized my mistake. Sorry, this was addition. I goofed. It's 7. Sorry about that. I was so busy with the radicals, I forgot to notice the sign. It's 7. Sorry. All right, so yes, there was a plus. Okay, but yes, you can see it's 5 radical 5 plus 2 radical 5, which is 7 radical 5. All right. Now, let's see what we can do with this one. Now, look, you can see that there is a 5. 5 is one of the factors of 80. So let's investigate this. Okay. So we've got 6 radical 5 minus 3 times 4 times radical 5. 6 radical 5 minus 12 radical 5, of course, gives me negative 6 radical 5. Okay. That worked out rather well, I must say. Let's see. Now we have another one here that you can see that these at least both have a common factor of 10. So let's check that out. Equals 13 radical 9 radical 10 plus 5 radical 4 radical 10. Okay, I think we're looking good here. Equals 13 times 3 radical 10 plus 5 times 2 radical 10. So we've got 39 radical 10 plus 10 radical 10, 49 radical 10. Now 10 itself, the only factors of 10 are 1 and 10 and 2 and 5, all of which are prime numbers. So we can't do anything with that. So our final answer is 49 radical 10. All right, now these last few are, we're going to have to rationalize the denominator and simplify. If you notice, in each of these cases, we have a radical in the denominator, which we always like to avoid whenever possible. So what do we do with this one, for example? Well, we always can multiply any number by 1 without changing its value. But here, the specific choice of 1 would be radical 5 over radical 5, because you can see what's going to happen. Oh, yeah, look at that. It isn't really, I mean, simpler in the sense that it still has a ratio, but at least the radical is in the numerator, which is one of our objectives here. So a mathematician would define that as simpler than 1 over radical 5. All right, now, what about this one? 3 over radical 8. 3 over radical 8. This time we'll multiply by radical 8 over radical 8. It's always, this ratio is always this number divided by itself. Okay, so 3 radical 8 over 8. Now, here's the thing though. We can take it one step further by recognizing that 8 is 4 times 2. And so what happens if we keep going is that we'll have 3 times 2 radical 2 over 8, 6 radical 2 over 8 equals 3 radical 2 over 4. And that's as simple as it's going to get. All right. Now, how about this one? Whoops. So, of course, again, we're multiplying this expression by the square root of 6 over square root of 6, because that's what we have in the denominator. And this is what we end up with. And of course, 3/6 is 1/2. And that is the final result. Okay, what about this one? Well, the first thing we're going to do is multiply this by radical 20 over radical 20. Okay, now that leaves us with 10 radical 20 over 20, which is radical 20 over 2, but we're not done, because look what we have. Okay, look what happened. These drop out, and we're just going to wind up with radical 5 by itself. So I would say that's really nice and simple compared to what we started out with. Now, something like this, let's see what we can do with it. Multiply it. Well, first, let's rewrite it like this. So 3 times 28 is 84. Let's see if 84 can be broken down into factors that are perfect squares. Well, let's see. What do we have hiding in there? I know. 4 times 21. So we're going to end up with, oops, sorry, I wrote it wrong. Both of these need to be under the square root sign. That's better. So we have 2 radical 21 over 28. And so that simplifies to radical 21 over 14. And there's nothing else we can do with it. 21, the only factors are 7 and 3, and 1 and 21, of course. And so those are all prime numbers, and so we're done with it. All right, well, there's only 2 left. Now, this one is really straightforward because look what it is. Well, that was easy. Now, this last one, in fact, we didn't even have to rationalize it. It just turns out to be 1/3. This one, let's see what it does. So we'll turn this into radical 2 over radical 3. And we'll multiply that by radical 3 over radical 3. And you know what? There's nothing we can do with this one. The factors of 6 are all prime numbers, so we're done. Well, that was that. So we now are experts in rationalizing denominators and dealing with radicals and identifying irrational numbers. Excellent. And of course, when the first test eventually rolls around, it'll be, a lot of the same content will be on there. So if you understood what we did today, you'll be in good shape. Of course, I will be posting these solutions on Moodle, so you can go double check them as much as you like, and go through and make sure you can get all these answers if you didn't already. In the meantime, we have a lot more fun new stuff to do, by which I mean finishing up chapter 5C. And by the way, I think we're definitely finish up 5C today. So what I'd like you to do, I think we mentioned this earlier, is take a look at the third and final problem set in chapter 5. Now, this one is pretty long. it wraps up basically all the rest, the exponents. Oh, maybe it's not as long as I thought, but no, that's pretty long. I think we can all agree that 55 questions is long, but you know what? Once you're done with this, you'll be in excellent shape for the next test. Okay, so that's what it looks like. So let's try to do this next Monday. So you got a long time to get it done. All right, in the meantime, let's go back to 5C, arithmetic sequences. We just barely started to look at this topic. The two basic types are arithmetic and geometric, and we've already mentioned that arithmetic sequences are ones in which there's a constant difference between the terms. Okay, so you can start anywhere, but here, for example, the common difference is 1, because every time I have a term, I add 1 to get to the next term. For this one, the common difference is clearly 3, because I'm just adding 3 as I go along the sequence. And then finally here, this is an interesting case because the numbers are going down, and that's because the common difference is -1. And I do want to mention too, the common difference doesn't have to be an integer. You could have something like this going on. Let's say 17 halves, 16 halves, 15 halves, 14 halves, etc. You can see that here, not only is the difference a fraction, but it's negative. So you can have negative differences and you can have fractional differences. So just be aware of that. Now, what happens if we have a sequence and we're looking for a specific term in that sequence? We could write them all out, but what if we're looking for the 500th term, for example? That could take a long time. So instead, fortunately, we have these formulas that will come to our rescue. And they're going to take a little getting used to, but they're not that bad. Let's look at the first one. Okay, so A1, now remember, A is used to represent a term in the sequence. AI equals term I in the sequence. The elements in the sequence are often referred to as terms. So A1 means the first term. N, now N is the number of terms, or the number of the term that we're looking for. You do? Okay, good. Yes, you may have seen this before. Oh, you did? I did not know that. Well, that's good. That means it's stuck in your memory and you won't have a problem. Excellent. No, I couldn't be sure if anyone had seen this before. So, well, that's good. But anyway, this N is the number of the term that we are looking for. And so this N is the same thing. This we will call it the nth term because we don't know what it actually is just yet. And D, of course, is the common difference. So now it's understood that we know what the first term is and what the difference is before we attempt to do this formula. But it literally can help us find any term that we're looking for. So now let's try it. In this case, for example, what is the 10th term of the sequence? All right, so the formula, let me remind you, is this. So A1 is here. N is 10 because we're looking for the 10th term. And you can see that the common difference is 5 because we go from one term to the next, we're continuously adding 5. And so we have 1 plus 9 times 5 And that equals 1 plus 45, which is 46. So this is saying that rather than counting them all out, you can just say, all right, well, let's use the formula. And we have 46 for our 10th term. Now, in the next slide, I've written them all out just to prove it. And you can do that too if you want to, as long as it's not ridiculously high, like 500. But on the test and on these problem sets, I don't have any like that. They're all fairly low, like look for the 8th term or the 9th term or the 12th term or something like that. So in that case, you can always feel free to double check your work because it won't take that long. All right, so let's see the proof. Let's write this out. And then, so in the next slide, like I said, it's just a list, and you'll see the 10th term is in fact 46. That's it. All right, number 10 is 46. Okay. How about this one? What's the 9th term in this sequence? So A1 is this one. N is 9. The common difference between the terms is 4. And so A9 is 2 plus, the first term is 2, 9 minus 1 times 4. So you got 2 plus 32, 34. All right, so in a second, when you're done with this, I'm going to scroll ahead and I'll show you on the next slide that it is in fact 34. Literally just by listing them out, you can find that the 9th term is 34. All right, so if we're ready, let's go ahead and look. Oh, I didn't write them out. Oh, okay, let's do it right here. I thought I did. All right, so then the next one would have been, let's see, let's write it out down here. And yes, this is the 9th term. 1, 2, 3, 4, 5, 6, 7, 8, 9. That is the one. All right, now here's another interesting application of this. What if I don't really need to know the nth term, but what if I want to know the sum of the first n terms for some reason? Let's say, for example, oh, I don't know. Suppose I'm playing some game where every time I win, the prize goes up by $1. Hold on a second. I'm going to throw this example in here real fast. So, in other words, we have a game where you play, and the prizes, the sequence represents the prizes when n consecutive, I don't know, games are won. Okay, so in other words, you're playing a game where if you win the first game, you get $1. If you win again, you get 2, 3. It's not a very exciting game, but what I want to know here is what if I win 5 times in a row? So in other words, I guess I'm not really explaining this very well. What this means is that if you win, let's say if you win on the first win, you get $1. On the second one, you get $2. On this third one, you get $3. On the fourth one, you get $4. And on the fifth one, you get $5. So therefore, if I win 5 times, I'm not winning $5. I'm winning all of these. Okay, that's what I'm trying to get across here. And I don't think I explained that very well. If I win 5 times in a row, I will have won not just $5, but 1 plus 2 plus 3 plus 4 plus 5, which is 15. So that is the sum of the first 5 terms. This is something that could be important, but you can see adding these together is kind of a nuisance. It would be nice if we had a formula that could do this for us. So it turns out that there is. It's a little bit messier than what we just saw, but it will do the job. And that's, of course, all that we can ask for, a formula that works. Okay, what else do we want? So let's take a look at this thing. Right there. So S means sum, Sn means sum of first n terms. Now keep in mind, this only works for an arithmetic sequence. And of course, we know what n means. This is term 1. And this is the nth term. And then whatever that is, we divide by 2. So why don't we do an example of this? All right. So I'm going to copy this formula onto each page so we can have a permanent reference to it, so we don't have to keep scrolling back and looking through our notes. All right. So let's try, let's say, this next one. And what I'm going to ask for is the sum of the first 5 terms. Okay. So I have the answer on the next slide. Let's look at for the first 5 terms. Okay, n is 5, a1 is 1, a5 is 9. And that's all that I need. So the sum of the first 5 is 5 times 1 plus 9 over 2, which is 5 times 10 over 2, 50 halves, which is, of course, 25. So that what this is saying is that the sum of these 5 terms should be 25. Is that true? Let's find out. Take out your calculator. Let's see. Yes, that's right, 25. So the formula took the place of manually adding up the first 5 terms. And again, you can see the advantage of this will be more pronounced when we have more and more terms. If we had to add up the first 100 terms, for example, then this becomes much more important than if it's just the first 5, let's say. All right. How about this one? We're going to look for the first 6 terms. Okay. The sum of the first 6. We see that what they are. So we know that, so n is 6. This is a1. This is A6. And so we're going to add them up by doing the following. 6, 8 times 8 plus 18 all over 2. 6 times 26 over 2. Let's see. Oops. Okay. So then if you want to, you can confirm this by just adding them together with your calculator. And you'll see that it is in fact 78. All right, now I'm going to show you why this formula works, but it will give me an excuse to incorporate a little bit of math history while I'm doing this. Okay, so maybe I can find a video about this too. I'll look into that. But in the meantime, I'm going to show you, this is a story from the history of math. So we have one of the greatest mathematicians of all time was named Carl Gauss, and he lived in, I'm going to say, from the late 1700s. Let me double check this real fast. Around the time of the American Revolution, I think he was born. So let me just confirm this. 1777, right there, almost exactly. Look at that, right on the dot, the American Revolution. And he lived for about 77 years. And he would turn out to be one of the greatest mathematicians in history. But he was, as you can probably imagine, a very bright student. Going back to his early days in school, it was very clear that he was a mathematical genius. And so the story goes that one day in one of his classes, one of his teachers decided to give the kids in the class a project. Now, this is when he's like 8, 9 years old at the most. The teacher says, all right, class, here's your project. Take all the numbers from 1 to 100 and add them up. Whoever gets there first gets a prize. Okay, so of course the kids were like, well, yeah, great, let's see who can win this prize. And they all take out a piece of paper and they start adding them up. Well, not Carl, not little Carl. Carl all of a sudden shows up at the teacher's desk within a matter of minutes and he says, look, teacher, it's 50-50. And the teacher says, how in the world did you do that so fast? He says, well, I was looking at the numbers and I noticed something interesting. If you write them out in a sequence like this, if you add up 1 and 100, you'll get a sum of 101. If you then add up 2 and 99, you get 101. If you add up 3 and 98, you get 101. If you add up 4 and 97, you get 101. So there are 50 pairs of numbers, each with a sum of 101. So the sum, or the total, must be 50 times 101, which is 50-50. So, of course, the teacher was impressed with him, but if you look at this formula, that's exactly what we're doing here, isn't it? If you apply this to the case that we just looked at, there are 100 terms, and each one, the first one is 1, the last one is 100. And here we've got 100 divided by 2, which means we have 50 times 101. So this formula proves that Gauss was right. But of course, he came up with this idea all on his own when he was a child in elementary school, which was a clear sign that he was going to become a mathematical genius, which he certainly was. So I thought you'd find that interesting. So, but that, I hope it helps you understand the logic behind this formula. You're trying to essentially figure out how many pairs of numbers you have with a given sum. Wow, how impressive was that? Not something that we mere mortals would think of when we're 6 or 8 years old, or whatever he was. All right, well, anyway, now we're ready for geometric sequences. These are a little bit more challenging than the arithmetic ones. And what's different here is, well, let me show you. Take a look at these. Now you notice right away, these are not arithmetic sequences. They're growing too quickly, but what exactly is happening here? How am I going from one term to the next in this sequence? What's that pattern? Well, in this case, I'm multiplying each, there you go, somebody got it, times 2. All right, so we say that we have here a common ratio, it's called, not a difference. We're going to call that R. What about here? What's the common ratio down here? Ooh, don't be shy. What's the common ratio? 3, exactly. How about this one? 5, precisely, yes. So you get the idea. Here, instead of adding a constant number, we're multiplying by a constant number. And you can see it's getting big fast. And that's how you can recognize it right away. You say, oh my God, look how big these numbers are getting. So I do want to point out here that just like with the arithmetic sequences, the ratio can be a fraction. For example, you could have 1, a half, a quarter, an eighth, a 16th. What common ratio do we have now? Ooh. I see a blank chat. Here we go. Nice. A half, exactly. And they can be negative too. Let's say I have something like this. 2, -4, 8, -16, 32. What's going on here? Why are they flipping signs like that? -2, precisely. Because it's all obviously 2, but because it's negative, every other one is negative and every other one is positive. And then we can combine them and we can have negative fractions too. So anything can be a common ratio. I mean, if we really wanted to get carried away, we could have a radical or anything we want, but we'll try to stick with the integers for the most part, or very simple fractions. Now, just like before, we would like to have a formula that will help us identify a particular term, and we do in fact have one. You can tell this applies to the geometric sequences because there's no D in here, but instead we have an R. Okay, so that R is the common ratio. N is the term that we are looking for. So we'll call that the nth term. Well, actually, no, this is the nth term, sorry. Let's think of this N as the term that we are looking for. And then this is obviously the first term. Okay, so if anything, surprisingly enough, this form is a little bit simpler than the one for the arithmetic sequences. All right, so let's see how this works out. So I'll put this up here somewhere. Just to keep an eye on it. So In this case, here's our geometric sequence. Why don't you go ahead and on your piece of paper, tell me what is the seventh term in this sequence using that formula. Now, if you want to double check, feel free to write out the next few terms. That's fine. But I'd like you to use the formula just to get some practice with it. So take a minute and tell me, what is the seventh term of this sequence? Up, here we go. 64, that is exactly right. So let's prove it. That's correct, exactly, 64, perfect. We have, if I had a prize, I would give it to you, but I don't. Okay, anyway, so AN is what we're looking for. A1 is 1. The common ratio is 2. N, in this case, we're looking for the seventh term. N is 7. So therefore, we have an exponent of 7 minus 1. So this all simplifies to 2 to the 6th. And if you throw that into your calculator, you'll see that it is, in fact, 64. Or the other option is to do this. Let me move this down here. Just start writing out the rest of the terms, and you'll say, oh, wait a minute, here it is right here. The seventh term is 64. Wow, how cool is that? You may have seen, like when you were in let's say, whatever grade it was, a puzzle. Oh, here we go. It is very cool, isn't it? You'll see it eventually where they'll say, listen, you've got the choice between two prizes, or let's say how about this one? You start a new job and you can either get paid $1,000 a week, or here's what we'll do for you. We'll pay you $1 in the first day of the month. Then the next day we'll pay you $2 and then $3. I'm sorry, $4 and then $8 and then $16. And it'll keep doubling. And you say, well, that sounds kind of bad. I'll just take the $1,000 a week. But it turns out that doubling for the whole month will actually give you more money than the $1,000 a week, because when you're doubling like that, it grows very, very quickly. So, in fact, this is how people ultimately are able to save for their retirements, because, I mean, the numbers don't grow this fast, but if you have your money in the bank for like 30, 40 years, it really grows like crazy. So anyway, and that's because it's basically a geometric sequence. The amount of money in your account follows this particular progress, depending on what interest rate you are earning. Let's see, I think there's another example here. Here it is. Whoa. Let's try this one for the fifth term. Okay, well, I mean, this one's pretty obvious, but go ahead and do it with the formula. All right, anybody have an answer? 243, exactly. So you can do it in one of two ways. You recognize that here the R is 3, and that means you just need one more term. Or if you use this formula, A5 equals, A1 is here, R is 3, the exponent is n minus 1, 5 minus 1. And here, if you recall from the product rule with exponents, there's an implied 1 here. So this is actually 3 to the 1 plus 4 power. And 3 to the 5th is, in fact, 243. Excellent. Now, what's missing? What have we not? Oh, that's right. There should be a formula now that lets us calculate the sum of the first n terms. And well, there certainly is such a formula. Let's take a look at it. And it's going to look a little scary, but no, not that much. So if you want to calculate the sum of the first n terms of a sequence, this is the way to go. Now here, there's only really two things. Well, three really. It's the first term. N is the term that we're looking for. Well, actually, no, I shouldn't say that. The term that you were looking, whose sum, all right, how about this? Trying to think of a good way to say this in terms of English. Let's just express it as you are searching or looking for the sum of the first n terms. And of course, this is the sum. R is the common ratio. All right, so let's move this on to the next slide. Whoops. So we've got this sequence, and we're going to look for the for some of the first 4 terms. Okay. So n is 4 in this case. So why don't you take out your paper and figure out the sum of the first. Now you can feel free to double check by just adding these up yourself, but I'd like you to use the formula. All right, any numbers? Anyone have that number? All right, we'll start filling in the numbers. So A1 is 5. The common ratio, I'm sure you noticed, is 2. N is 4. So yeah, it's a bit messy, but you've got 5 times, now 2 to the 4th is 16. So you've got 5 times negative 15 over negative 1. The negatives drop out, they cancel out, and we have 75. And of course, if you add them together, you'll see the same thing. It's 75. So that wasn't too painful, was it? No. And yeah, so that's it. So this section is done now. So that means we're definitely going to do the third problem set from chapter 5 on Monday, because now you're ready for it. You've got all this background done. And so that means we do have a little extra time today to at least take a peek at chapter 6. Okay, so let me go get that off of Moodle. There's our old friend Carl Gauss again. All right, don't forget that name. So what am I doing here? This is pre-calc. What am I doing? So 6. Now 6 is kind of an extension of 5. Some of this material you may have seen before, some of it maybe not. And so in the beginning, we're going to look at some concepts that you're probably very familiar with. Just a brief review of some of the principles of algebra, where we're basically trying to learn how to simplify and evaluate expressions. There's a little bit of vocabulary here that you should already be familiar with, but it's possible you've started to forget. So for example, a variable, of course, is any quantity that can change. Ordinarily, we express that as x or y or possibly z. An algebraic expression is a combination of variables, constants, and operations. Now, operations means multiplication, addition, subtraction, exponentiation, and all the rest. A constant, and by the way, the reason why we have this idea is, let's say you have 3x squared plus 7. This is not an equation. It is not set equal to some constant. So we call this an expression to distinguish it from an equation. If I set this equal to 0, it becomes an equation, but right now it is an expression. And it does contain a variable x. It has a constant, which is 7. And it also has what's called a coefficient. The number that is multiplying x is called a coefficient. And of course, we all know that this little 2 up here is the exponent. All right, so within any algebraic expression, you could have any or all of these components, a variable, a constant, an exponent, and a coefficient. I almost forgot, we also have the operator. Plus is the operator in this expression. Okay. And of course, the word operator simply means it is telling you to combine these terms in some way. All right, so I don't think any of this comes as a surprise to anyone. It's just that you may have started to forget some of these words. So anyway, I guess we're ready for the next slide. Here's one that's a little bit tricky. This is your expression right here. Now, I do want to point out, when you have something like this, there's an implied coefficient of 1 here. We don't always write it like that. We just leave it as x, but there's an implied coefficient of 1. And if you have something like this, just plain y by itself, let's say, there's an implied exponent of 1. So this expression, it has three terms, they're called. And so the coefficient of the first term is 1. The second term has a coefficient of 3, and the last one is 2. And this x1 and y1, there's an implied 1 associated with each one. Each one has an exponent of 1. All right, everyone sees what's going on here? So we have coefficients, exponents, variables, constants. Actually, there's no constant here, sorry. You could think of the constant as being 0, but this is what we have. Oh, and the only operator we have is plus. There doesn't have to be an operator, by the way. Something like this by itself is an expression, even though there's no operations going on. All right, now we're going to see how, and this is something we discussed in the last chapter, we're going to revisit an old friend of ours, the distributive property. Okay, now here we're not going to typically wind up with constants, but we do know that something like this tells us this is the distributive property of multiplication over addition, and it means multiply 3 by each of these terms and add up the results. Okay, so you'll end up with 3x plus 3 times 2y, and ultimately that becomes 3x plus 6y. The same thing holds here, except you've got that negative to deal with. So here we're going to have negative 4 times 2x minus 4 times negative y. And so you got to be careful with those negatives. So the first term will become negative 8x, but the second term becomes positive 4y. Because when you multiply negative by negative, of course, you wind up with a positive. All right. Now we're going to then use this result, among others, to help us simplify algebraic expressions. So if you notice so far, this common theme between everything that we've done, we always want to simplify our results whenever possible by whatever means are available to us. Simplifying is in a way, I mean, mathematicians see simplification as making the results more clear. And that's what we always want. The more simple the result is, the clearer it will be. And so with algebraic expressions, we want to do the same thing. It's not just radicals. All right, here we go. So let's look at some of these. Now, first, one of our strategies is to combine what we call like terms. And that typically means here terms that have common exponents. All right, well, we'll see what I mean in a second. Like, let's say, for example, you had something like this. You've got 3x squared plus 4x plus 7x squared plus 5x. You wouldn't just leave it like that. What would you do? These are considered to be like terms because they both involve x squared. And these are also considered to be like terms because they both involve an x. So you consolidate the like terms with each other, and you end up with this much nicer result. Okay, so just look for any what we call like terms, and constants would be considered like terms as well. That's what we're being asked to do here. Simpler is always better. All right, so let's look at some quick examples of this where they're a little bit simpler actually, but they may involve the distributive property. All right. This one, well, that's a very simple case. The only like terms are these two. So we'll add them together. Look, we've got, this actually is 3 minus 5. Minus 5, there's a negative here, is all multiplied by x. So you end up with negative 2x plus 2. Look how nice that is compared to what we started out with. All right, let's see what else we have here. Oh, here's a messy one. Now, how many like terms do we have here? We've got some x squares, and we have some x's. The constant is sitting there by itself. There's nothing we can do with that, but we can certainly consolidate the x squared terms and the x's. So let's do that. Remember here, there's an implied coefficient of 1. Over here for the x's, we have the 8 and the negative 2. So you can see that we're going to wind up with 4x squared plus 6x plus 5, which obviously is a much nicer result than what we had up here. And also notice that the order of the exponents is from high to low. We always had the highest exponents on the left, and then we put the lower ones as we go along to the right. That's just by convention. I think, we can all agree that it looks better than this. I don't know. I guess maybe it's because we've been trained to look at it that way since we were little kids, but this is the way to go with this type of expression. All right. So let's see if there's any more examples of this. Of course, as we know, more practice is always better. Ooh, look at this one. We've got, but it's like terms here, like terms here. The constant is still by itself. So we consolidate the x cubes and the x squares. Okay, so you're going to wind up with negative 3x cubed plus 9x squared plus 3, and you're done. All right. Well, that was interesting. Now, the next thing we're going to look at is this idea of evaluating expressions. Okay, so here we're just consolidating them. We're not trying to come up with a specific number. In order to do that, we're going to have to do something called evaluating the expressions. So, like, here's an example. Suppose that when you walked into the store, you were told that the product that you're trying to buy will cost this much. In other words, what they're saying is that each item you buy will cost $9, but today we'll give you a $2 discount for coming into the store. How about that? Okay. So if you wanted to buy 3 units of this product, that means you just simply plug in the 3 into the X, and you see that you're actually going to pay $25 to buy 9 units. Okay, $9 each, but here's the discount of $2. And so the total cost is $25. So what you've done is you've taken an algebraic expression and turn it into a constant by choosing a specific value for X. That's what we mean by evaluating. And so it's straightforward in the sense that all you're doing is replacing all the X's with a constant and solving for it. And of course, in the real world, when the math is fun and all, but you at some point you want to use it for something specific, like figuring out how much profit you make from selling 100 units of your product, for example, or how much does it cost to produce 100 units of this product. So let's see, there's another one here that I'd like you to look at. Oh, now this one's a little bit more challenging because you've got an x squared in there. So what is the value of this expression when x equals 2? Well, again, just make sure that you replace all the x's with 2's and then just work on the results. And in this case, you can see that it worked out to be 2. All right, one more. This one's a little different because, well, you'll see right away why. Look what happened here. You've got 2 variables, and that can actually happen. And if that happens, you must supply a value for both x and y. Okay, so here you've got 2 variables in your equation. So you replace all the x's with 1 and all the y's with 0, and you will wind up with a result. In this case, it's 13. Okay, so it is possible. We're not going to see too many of those, but it is always possible to have more than one variable in an expression. And so therefore, to evaluate it, you must provide a value for each individual variable. And that's all you have to do. All right. Well, you know what? I think we don't want to push our luck today. We will stop right here. Don't forget to work on problem set number 3 for next Monday. And of course, this will be it's a fairly long one, but it's excellent, excellent practice. All right, so now, by the way, I see the snowflakes are coming. It's starting. The deluge is beginning. So I hope you don't have to go anywhere today. Or if you do it now. So from what I understand, it's going to get ugly. So anyway, all right. So unless there's any last minute questions, I'll see you on Monday when hopefully we're dug out of this mess. All right.
Thank you.
Thank you.
Later.
Thank you. Have a nice week.
Bye.